Okay, thank you very much. I'm Taira from the University of Tokyo and RIKEN, and I'm very very happy to come to Milano finally. And today I'd like to give a talk about online learning and game theory, figure out lower bounds and adaptive learning dynamics. So this talk is about basically learning games where there are several players in a shared environment, each aiming to maximize their cumulative reward based on past observation they can observe as a result of interaction with other players. And why do we consider this problem? Because it has wider applications in machine learning. For example, it's related to minimax optimization, variation inequalities, and it's also related to multi-agent RL. And more recently, it's used for developing superhuman AI for board games. And more recently, it's used even for running large language models. So these are motivations. And in particular, in this book, we focus on the classical setting of two-player just-sum games. And before explaining the learning games formulation, I'd like to recap several notions of two-player just-sum games. In this setup, there are two players, an X and Y player, each having MX and MY actions. And this game is characterized by a known payoff matrix A, which is an X by MY matrix with entries between -1 and 1. And one of the most famous example to play some game is rock, paper, scissors. For example, here there are X and Y players, each having 3 actions, rock, paper, and scissors. And for example, if X player chooses a rock and Y player chooses a rock, the payoff for both players is 0. And X player chooses a rock and Y player chooses a scissors. Since the X player wins, X player gains 1 as a reward, and Y players gains -1 as a reward. So since this is a zero sum, one can express this game by using the red characters only. And so this is an example payoff matrix. And more generally, two-player zero-sum games can be formulated something like this. First, X and Y player chooses the strategies, X and Y, which probability distribution over the action sets. And then X player gains a reward of X transpose AY, and Y player incurs a loss of the same amount. So this is a zero-sum game. Intuition of X transpose AY is we assume that X and Y player chooses their actions following the strategies X and Y. So under that assumption, X transpose AY is an expected reward for the X player. So in two-player zero-sum games, we tend to consider a notion of Nash recursion, which is informally a pair of strategies in which no player has an incentive to deviate from that pair. But basically, the classical formulation of two-player zero-sum games assumes that payoff matrix A is known before the game starts. But we maybe not have exact information of payoff matrix A before the game starts. So ideally, we would like to get compute a Nash equation without knowing the payoff matrix A. So this is one motivation for running in games. And so learning in two-player zero-sum games is a sequential formulation of two-player zero-sum games, which is again characterized by a payoff matrix A, but this is unknown in this case. And recall that payoff matrix A is a MX by MX matrix, and the entries are between -1 and 1. And in this setup for each time step t, each player chooses the strategies xt and yt, which are probability distribution over the action sets. And then X player gains a reward of xt transpose ayt, and Y player incurs a loss of the same amount. This is the same as previous two-player zero-sum games formulation. And the difference is in the third lines. Finally, in the last step, X player and Y player observe their gradient feedback, GT equal AYT, for the X player, and the LT equals A transpose XT for the Y player. So what is this? This is just a kind of gradient of the saddle point optimization characterized by payoff matrix A. If we consider this kind of bilinear form of saddle point optimization, then for the X player, AYT is a gradient, and for the Y player, minus A transpose XT is a gradient. So this is a motivation for these observations. And as you can imagine from the name of the games, goal of both players are to maximize their cumulative reward. And interestingly, this problem of running into players of some games has a deep connection with online learning, online convex optimization. In the second line, we can see that X player's gain can be written as the inner product of the XT and GT, and Y player's loss can be written as the inner product of YT and LT. So for both players, they are observing the gradient vector GT or LT, and they are trying to maximize their cumulative reward based on these observations. So for each player, this problem can be seen as online linear optimization over the probability simplex. And one can define the legalet in the context in games as similarly to the standard online learning. So the goal of each player is now to minimize the external regret of X and Y players. And the reason why we care about regret is its classical connection with Nash equivalent. So red X bar T and Y bar T be the average plays of X and Y players over large T rounds. Then what's known is this X bar T and Y bar T, the product distribution based on X bar T and Y bar T is an approximate Nash equivalent. And here error is upper bounded by the sum of the regret divided by large T. So what this say is, if we use a standard line learning algorithm, the regret can be upper bounded by square root T. So this implies that we can get the convergence rate of 1 over square root T to Nash equivalent. So now we are interested in if this convergence rate is optimal in games. In online learning, we cannot get better rate. In online learning, one can construct an instance where we cannot improve the regret upper bound of square root T. But what happens in the case of games? In fact, it's known that we can improve the legalet. So naively, one can consider Hedge algorithm, something like this, as an algorithm for X and Y players, which leads to 1 over square root T convergence rate to a Nash equivalent. And what's known from 2013 is one can modify the Hedge algorithm a little bit to get better convergence rate. What this do is to exploit the most recent observation twice to compute the strategy. So for example, for the X player, they use the most recent observation GT minus 1 to compute the to get the strategies. And for the Y player, they use T minus 1 to compute the strategies. And what's known in the literature is if both X and Y players completely follow optimistic hedge with a constant running rate, the regret of X and Y players are bounded by log of the numbers of actions of X player times that of the Y player. So this implies log mx my divided by T convergence rate to a Nash equivalent. Intuitively, what they say is in standard online learning, we cannot improve the square root T upper bound since the opponent, the gradient can be arbitrary. But in the case of games, if we know that the opponent is using the no-regret learning algorithm, it's kind of online gradient descent, so one can one can predict the next round's true loss using the most recent observation. That's interesting for getting the better rates. And again, what this theorem say is if X and Y player completely follow optimistic hedge with a constant running rate, then under the assumption that the payoff matrix A is between -1 and 1, one can get this convergence rate. And this is known to be optimal in terms of large T. So this looks very, very good, but this raises 3 natural questions. The first question is the dependence on the number of actions mx and my optimal? We have log mx and y here, but is this dependence optimal? And the second question is, what if the opponent deviates from the given algorithm, optimistic hedge? We in this theorem, we assume that both players use optimistic hedge with a constant running rate. But what happens if, for example, y player deviates from this algorithm? And the third question is, this theorem assumes that the payoff is between -1 and 1. But what happens? Can we get the first convergence rate without knowing the scale? So we investigated these 3 questions recently. So let me briefly introduce these results. So the first question is on optimal dependence on the number of actions. And because that we get this convergence rate. And what we show recently is this result, this regret upper bound can be input to the square root of log of mx and times log my, which is particularly important. This improvement is particularly important when log mx and log my are imbalanced. For example, when the number of actions of x player is exponentially larger than that of the other player. And what we also show is this rate is optimal for optimistic hedge with a constant learning rate. This partially resolves the question raised in 2024 papers on optimistic hedge with on the number of actions of for optimistic hedge. And I'm not going to give a detail, but we also investigated the convex reformulation of regret upper bounds to get the optimal rate, and also dynamic regret. Investigated dynamic regret, which has a deep connection with last iterate convergence, and provide regret upper and lower bounds for dynamic regret. And we also extended to the Helder smooth convex concave games. And the second question was, what if the opponent deviates? As one can imagine, if we use a constant running rate, then the player may suffer a linear regret because the running rate is constant. And there is one solution to this. There is one solution to remove this, to avoid this linear regret, which is we monitor the gradient variation, and if it exceeds a certain threshold, and switch to algorithm with square root regret. So this is one solution. What they say is consider the figure where a horizontal axis is amount of deviation by the y player, and the vertical axis is regret of the x player. And what this known solution gives is in the honest regime, where every player follows the optimistic hedge, then the regret of x player is bounded by a constant. But as the amount of deviation by the y player increases, the regret of x player jumps to the square root t. So this is discontinuous behavior, and it is not desirable. And to deal with this, we construct a new running dynamic that is robust against the deviation by the opponent player. In particular, we show that there exists a running dynamic such that the regret of x player is upper bounded by square root of the y player's cumulative deviation plus the linear term of x player's cumulative deviation. So, and the same for regret of the y player. The regret of y player is upper bounded by a square root of deviation by the x player, which is opponent player for the y player, plus the linear term of the deviation by the y player. So what this say is if each player follows a given algorithm, they don't suffer linear regret. Even if the opponents, if the X player follows completely the given algorithm, then this term becomes 0, and this even the Y player completely ignores a given algorithm, the regret of X player is upper bounded by square root t. So this is desirable then optimist state with a constant running rate. And we also show that, in fact, this is a quite informal statement, but we show that for any running dynamics, there exists a game with where the X player's deviation is upper bounded by Cx and the Y player's deviation is upper bounded by Cy, such that the regret of X player is lower bounded by the square root of deviation by the opponent plus the linear term of its deviation. So upper bound and lower bound match after logarithmic terms. And the final question was, is scale-free first convergence possible? And recall that what is known in the literature is if A max, which is a range of payoff matrix, is known before the game starts, we can get this convergence rate. And to investigate this, we introduce a notion of scale-free learning dynamics, which is quite similar to scale-free online learning, which is informally requires no knowledge of the payoff scale before the game starts. And also, what they say is if payoffs are scaled by any positive constancy, the strategy sequence is unchanged. This property has been known as a very key property for the success of regret matching, which is one of the most good algorithms for extensive folk games. And what we show recently is there exists a scale-free online learning dynamics such that for any games with a payoff matrix with scale between minus A max and A max, we can get approximate natural equivalent with a convergence rate of A max divided by large T. So this rate is the same as the rate when we can get when A max is known before the game starts. And for the paper 2 and paper 3, actually there are more interesting results in the paper, which is extension to multiplayer zero-sum games. This is closely related to so in multiplayer zero-sum games, we tend to consider the notion of correlated equivalent, which can be obtained by we can see correlated equivalent can be obtained by the scenario where each player uses no swap regret minimization algorithms. And for multiplayer zero-sum games, for the paper 2, we constructed the crafted learning dynamics. And for swap regret minimization, we need to prepare a bunch of experts and integrate them as a Markov chain. We construct the Markov chain from the outputs of experts and use the stationary distribution of the Markov chain as a strategy of each player. And what we did is we did the stability analysis of Markov chain for optimistic FTRL with adaptive learning rates. And though it is not directly related to swap regret, but we are also dealing with adversarial corruption of the gradient feedback for the second paper. And for the third paper, we constructed learning dynamics with first convergence to correlated equivalent without knowing the scale. And in terms of technique, we introduced a new stopping time analysis to exploit the negative term, which is useful for obtaining the first convergence in games. And we also introduced a new technique, doubling creeping, which is a new scale-free online learning useful in swap regret minimization. So to summarize, key takeaway is first convergence in learning games is possible with dimension efficient and deviation robust and scale-free regret upper bounds. So yes, thanks for listening.
I'd like to introduce myself first. So I'm Kazuto Fukuchi, faculty member at the University of Tsukuba and visiting researcher at RIKEN AIP. I'm on the area security and privacy team organized by the Professor John Sakma. And my research interest is statistical learning theory about the data bias in machine learning. Like data bias is like we're constructing some model from the data, but the distribution of data is somehow skewed. For example, fairness is one problem of data bias, where the data is skewed by some socially sensitive information, and transfer learning is a distribution theft problem, and out of distribution generalization. So my recent result is about the data scaling law for transfer learning, as well as I have a fairness result about the min-max optimal fair regulation, and I have another fairness paper at ICML. So if you join the ICML in Seoul, it's nice to see you again. Today, I'd like to talk about the result about ELIAS stats. So this is a joint work with Ryuichi Hataya and Kota Matsui. So what we thinking of is pre-training. So this is nowadays a common technique for machine learning. So we were constructing the very, very large model using the bunch of the data set and constructing some model and use it to deal with some downstream task with a few sample. Like we have a creep model that is built on the bunch of data set, the bunch of the image data set, and use it to the medical data set, which the task, the sample is difficult to obtain because to obtain the data in the medical area, we need some professor need to collect the data from patient. And for example, the pre-trained model can be used for more complex tasks like the visual query question answering by combining the pre-trained text model and the visual model into the single model to answer some question to the image. So based on that, what we think is a scaling law for the pre-training. So scaling law is originally initiated by the Kaplan et al. That say the performance of the large language model scale is the several amount of the size, like a model size, a data size, and the amount of the computation. So specifically, we're focusing on the scaling, data scaling for the pre-training. I bought this picture from the Mikami et al. This picture shows the horizontal edges correspond to the downstream sample size, whereas the vertical edges correspond to the downstream error. And there is a 3 line here. The line corresponds to the model size of the pre-trained model size. So you can see that by increasing the downstream sample size, the error gets decreasing. And also we can see that by increasing the pre-trained model size, the error gets better. So that's kind of the scaling, like by increasing the pre-trained model size, downstream sample complexity gets better. So what we like to do is, can we construct a running theory to explain this behavior? So there is a many theory explain the success of the pre-training, like do et al. By et al. Kim et al. This is a working on the few shot adaptation. And it's basically derived this kind of the bound, error bound. So where the M stands for the pre-trained sample size and the N stands for the downstream sample size. And this form looks like the M2 minus alpha plus the N2 minus beta, where the alpha and the beta is some constant, but the beta is much larger than the alpha. So intuitively, without pre-training, the decreasing rate of the downstream task governed by the slower rate of the minus alpha. But by using the pre-trained model, the convergence rate of the downstream task gets a minus beta, which is more faster than minus alpha. So, but by visualizing this rate, we can get this picture where this is the same, the horizontal rate is corresponding to the downstream sample size, the vertical corresponding to the downstream error. And for the small L, small downstream sample size, this term is dominated, so the error gets decreasing. But at some time, this term gets dominated so that the error gets constant, saturated. So this is a wired behavior because we are carrying out the downstream learning. So by increasing the downstream sample size, we should get the decreasing behavior. So that's say this kind of theory cannot explain the data scaling law for the pre-training. So our desire is like this rate. So there is a N2 minus beta term as the same as the previous slide. And there is a small order one term, which means the term decreasing in the pre-training sample size. To visualize this rate, we can get this picture. So by increasing the pre-training sample size, the error rate gets better. So basically, we'd like to get this kind of the learning rate. So, okay, the question is, so basically in this paper, the constructing pre-trained learning algorithm is somewhat difficult. So what we do is clarifying the condition, sufficient condition for which pre-train can probably expect the data scaling or law of the disconvergence rate. So let me explain the prevalence setup. We are thinking of the pre-train and the downstream learning task. So we are using the M sample for constructing pre-training F3, and using the N sample to construct the regulator for the downstream task. So we assume the pre-training distribution and the downstream distribution are somehow different. And we also assume the regression model underlying to the distribution, where the outcome is some regression model of the covariate plus noise. And we evaluate error by the deviation from this underlying regression function. Then what I mean by the condition of the pre-training. So here we're thinking of this as a relationship between the pre-trained model and the underlying regression function. So the condition we think is named as a chokeability, where we are assuming that pre-trained model can be split in the head model and the feature extractor model, that this is a head model and this is a feature extractor model, combining it the result in the pre-trained model. And what the chokeability said, by inserting some adapter model in intermediate of this spirit, then the underlying function, regression function, can be recovered. So this is this can be intuitive because we can imagine what this structure means. So each data, so thinking of the data as an image, so feature extractor corresponds to the mapping from the data to the some manifold. And the head function is a function to calculate the level of the manifold. So what the adapter doing is, so there is a source, this manifold corresponds to source pre-trained distribution, and this manifold corresponding to the downstream distribution. So adapter model converted this manifold to this manifold. The adapter model has the functionality to convert this manifold to this manifold. So if the transition to this manifold is somewhat easy, the pre-train might be the successful. That's some kind of the imagination of this definition. And in addition to that, we're thinking of the decreasing complexity, where we are thinking as I said, we are thinking inserting some adapter model into the pre-trained model. And we are additionally assume the complexity of the adding adapter model gets smaller as the pre-trained sample size increases. This is assumption about the pre-trained learning algorithms. So we are assuming the pre-trained learning algorithms is designed to have this behavior. So what is the complexity? I'm using the standard coupling number and approximation error trade-off control of to characterize the complexity. And we assume that the adapter model we need is increasing complexity. So because the smaller beta here is correspond to more complex adapter model. So we are assuming the complexity of the adapter model increases up to beta. Then we are carrying out these algorithms of the empirical choking. This just doing the parameter efficient fine tuning of the adapter model. Just adjusting adapter model using the SWIFT risk estimator. So yeah, this framework covers the parameter efficient fine tuning method. So this is a main result that suppose the underlying model can be chokeable. That means by inserting adapter model, the underlying model can be recovered. And we assume the training algorithm is the decreasing complex tendency, and suppose the head model is alpha for the continuous. Then we get this kind of the band. So this actually explains the data scaling law, because this term is decreasing in the pre-trained sample size. So by as an increase of the pre-trained sample size, the decreasing rate of the downstream task get close to this exponent. So this is a fastest rate in this case. And experiments. So we are carrying out the experiments about the fine-tuning CNS and integrating the vision capability to the elements. So in both cases, so we are inserting MP layer, adapter layer with a varying depth into the different size model. So blue model is the blue line corresponding to the smaller model, and the orange line corresponding to the larger model. So the best error achieved for each the pre-trained model size is denoted by the star. So we can see that by using the larger pre-trained model, orange one, the number of the layer to achieve the best error is smaller. The best error can be achieved by the smaller layer compared to the more smaller pre-trained model. That's consistent with our theoretical result. To conclude, we're investigating the pre-training, and the motivation is to show the data scaling role. And we're introducing the chokeability, and which is inserting some adapter model. And if the complexity of the adapter model gets smaller, then the data scaling role can appear. And key takeaway might be our method is basically the parameter efficient fine tuning. This is some supportable theoretical justification of the parameter efficient fine tuning. And for future direction, so in this talk, we doesn't give any concrete pre-training algorithms, just writing some sufficient condition to achieve the data scaling law. But the question is, how should we pre-train? Can we end-to-end analysis to exhibit the provable data scale law? Actually, this is almost done, and the archive paper can be appear soon. And another question might be, will behave model adequately control the model complexity in the pre-training stage? Like attention is some kind of the controlling complexity by introducing the sparse structure, and also the orthogonality, like a muon, introduce some kind of the complexity, automatical complexity adjustment. They combine this kind of analysis to show the provable data scaling can be the interesting future direction. Okay, thank you. That's all on my talk.
Are there any questions? Yeah. Can you go back to the definition of this cokeability? Okay, how, I mean, yeah. How plausible is this? I mean, is this something that is used in like a way to obtain this kind of results, or is something justified by practice? And it's something that people use to prove something, or is something that has been observed, like emerged from practice?
I believe this is driven from some practice, like when constructing the vision language model, we are combine the text model and the vision model. The way is just inserting the adapter model. That's the source of my idea to come up with this definition. So I believe this is a practical strategy for
Okay, thank you.
Good afternoon, everybody. First of all, I have to thank you all for this interesting workshop that is full of theoretical machine learning. I'm coming from different area, which is wireless communications. Our topic title today is Smart Wireless Power Meets Intelligence, AI-driven RIS-SWIPT for IoT network. And RIS is reconfigurable intelligent surface, and the SWIPT is simultaneous wireless information power transfer. Both are two techniques that will be used in 6G for advanced signal processing. First of all, I belong to computational learning theory team. My group leader is Professor Kuihatano from Department of Informatics. And we are located in Kyushu Island, the southern island. And in Fukuoka, there is Kyushu University. And it have a nice, interesting camp. E2 campus, there is East Zone and West Zone. West Zone for engineering and chemical physics, and the East Zone for language and so on. Today's talk related publications, we have some accepted papers in Open Journal of Communication Society and in ICML-CN, it's International Conference on Machine Learning for Communication and Networking. And we have two papers under review now in IoT Journal and in OGCOM Journal 2. Our agenda today, we first have a quick introduction about 6G and IoT devices. Then we will talk shortly about SWIPT, RIS, and ISAC. And then we will have a case study about RIS-aided SWIPT and how the importance of RIS to enlarge the SWIPT area. And then we will have talk about ISAC-aided SWIPT. Then we will conclude and have some future directions. First of all, for the wireless communications, each 10 years we have new generation started from 1980. The first generation was landlines, and then second generation, 1990 was texting and SMS. And after that, third generation, 2000, it was internet access. And for 4G, we have also added video and mobile broadband. And the 5G, currently, we are working in. We have IoT, smart cities, wearable devices. We use the new bands like millimeter wave, terahertz. And now the way is to go launch 6G at 2030. And we have a fully digital connected world that is related to artificial intelligence, extended reality, and spatial perception, real-time control, and automated vehicles. So at each generation, there is key performance indicators. Our 6G key performance indicators, we have the big data rate should be larger than 1 terabit per second compared to 5G, which is 20 gigabit per second. And the latency is round trip delay should be less than 0.1 millisecond. And the mobility, the 6G should support 1,000 kilometers per hour. And we have cell-free multiple access techniques and RIS aided. And also the core network will depend on AI native 6G core network. And the key services will be AI, augmented reality, and holographic communication, and so on. To achieve such key performance indicators, we need some techniques, our technologies that solve or try to solve these, to achieve these key performance indicators. On behalf of the Internet of Things, now the number of connected devices are increasing in large. Here we don't include the computers or laptop or fixed point. We mean the IoT devices, and we classify it. For 2025, it's almost 24 billion devices, and it's increasing, and we have to handle all of these devices, as the power or the need of the power is the most important thing. This is a motivating example.
What does charging look like in the future? Imagine walking into a room and your phone automatically begins charging. Today, we're bringing this closer to reality. Introducing e-air charge technology. Using a system of 144 antennas, this transfers energy to the smartphone in the form of an extremely narrow millimeter-wide wave meter. Within a few meters, we offer 5 more remote charging solutions. Taking that a step further, it also supports multi-device charging, charge on the move while gaming, or even when something's in the way. Looking ahead, smart living goes truly wireless. This isn't science fiction. This is technology. Air charge technology.
For the near future, we will have some connecting devices or wireless charging while we are sitting in this room having the lecture. Our devices will be wirelessly charged. And I found some sites that have Nissan, for example, the car company launched wireless charge inside its car. And also there is some studies about the restaurants that will advertise about this technology and how the customers will be gathered or will visit this restaurant more regularly. Now we will have a short talk about SWIPT. It's simultaneous wireless information power transfer. Instead of sending the information only, we send information and energy harvesting. So the device that want to be charged can make use of this signal for harvesting. So we use the same radio frequency for information decoding and harvesting. It's important for IoT devices because IoT devices are battery constrained, low power, and massively deployed. And SWIPT will ensure sustainable operation and will reduce the battery replacement of these IoT devices and energy efficient 6G for IoT network. But there is some practical consideration, which is the realistic energy harvesting circuits are nonlinear, not linear. And this because of the diode behavior for translating the AC or to DC using diode. And this nonlinear energy harvesting will affect the beamforming, the resource allocation, and waveform optimization, and the achievable SWIPT performance. And we need some machine learning techniques that handle or solve these problems. There is 4 types of SWIPT receivers. The first one is separated, where the information receivers are separated from the energy receivers. The second one is time switching, which means we split the time between information and energy. And there is power splitting. We split the power. Part will be for the energy and part for information. And also antenna switching If we need information, it will be some antennas for information decoding and other for energy harvesting. Now we move to another technology, which is RIS, Reconfigurable Intelligent Surface, and some others calls it RIS. The idea, it's like a mirror or advertisement panel that have a small reflecting antenna element. So if the line of sight between the base station and the receiver are blocked, we can make use control of the line of sight using reflecting angles between the base station and the RIS, and then from the RIS to the receiver. The idea is to smart configure the wireless propagation environment, and for the sake of that, we use low-cost passive reflecting element on the planar surface. Now, why RIS technology appeared? It appeared because when the 5G have massive MIMO systems, which means the number of antennas on the base station are much larger than the mobile users. So it will increase the complexity, and we need more focused energy. And we support large number of users, but we have two main limitations in 5G, which we don't control the wireless channel because only we use the line of sight channel, not line of sight. And second, mounting this large antenna on the base station, we will have high power consumption on the wireless interface. So we started in RIS by passive RIS, which is only, it reflects the signal. And its advantage for SWIPT, it's low power and cost efficient. But with the years, there have been more types of RIS with more complexity. Active RIS, which includes amplifier inside, and also star RIS, which is simultaneous transmitting and receiving, which means that we make use of the reflected signal and the incident signal. So this will help to make use of the refracted and incident signal, which is reflected and refracted signal. Also, there is self-sustainable RIS, which contains energy harvesting. There is hybrid RIS, which means that in the same RIS we have either active or passive or star. And also there is beyond diagonal and extremely large RIS, which have a large number of antenna elements, and also multi-RIS. Now for the RIS-aided SWIPT, why? It's important because we need to support almost 31 billion devices, and the future IoT application will have will need reliable wireless connectivity and sustainable perpetual energy. So conventional battery replacement will not help in this. And for wireless power transfer, we need long range wireless charging, like the Xiaomi Mir Air videos that we saw. And if we use SWIPT only, it will have suffer from severe propagation loss and multiple fading and low end-to-end energy efficiency. And of course, a number of antenna elements are expensive, so the complexity will be increased. So we used RIS-aided SWIPT to increase the programmable wireless environment, to enhance signal focusing and beamforming, and of course to improve the energy harvesting and to extend the SWIPT coverage with low hardware cost. The third technology today is ISAC. ISAC is integrated sensing and communication. And instead of communicate and see the channel, we will sense the target too. So we have two options, communication and sensing in the same time. And we use the same spectrum and the hardware and the waveforms for both wireless communication and environmental sensing. And this is efficient spectrum utilization, and we reduce the hardware and energy cost. and it will be real-time environment, which is important for application like autonomous driving and support autonomous and intelligent systems. For the communication rate performance matrices, we have the rate, spectral efficiency, energy efficiency, SINR, signal to interference noise ratio, bit error rate, outage probability, and the latency, which is the delay between round trip of the signal. For the sensing performance matrix, we have the detection probability, the target detection capability, estimation accuracy, range resolution, angular resolution, localization error, and sensing coverage. And we have this trade-off between communication and sensing. If we improve the sensing accuracy, we will reduce the communication rate. And we need some techniques for joint waveform, beamforming, and resource optimizations. So a case study for this RIS-SWIPT, if we have access point that service energy harvesting and information users, and the signal will be transmitted, will have two parts. This is the information decoding signal, and this is the energy harvesting signal. And then the total transmit power will be the power of the precoding matrix for the information and the precoding matrix for the energy. And then the received power as a user will be the channel gain multiplied by the theta, which is a phase shift matrix of RIS, and F is the precoding. And this is the signal to interference noise ratio in that case, as the energy harvesting users will be like interference. So the received power as an energy harvesting user will be the same. And our target in this problem, we want to maximize the weighted sum power received by the energy users and subject to transmit power constraint at the access point and unit modulus phase shift constraint as the RIS and the individual SINR constraint as the information users. So our optimization problem will be like that. And we have some constraint on the SINR for quality of service and for the power for energy harvesting. And this problem, after some assumptions, will be reduced to such a problem, which is non-convex optimization. And it depends on most of the survey paper or previous work. They used alternate optimization to solve it, and including fractional programming, semi-definite relaxation. And our target is to find online learning solution for such problem. But today we will have some discussion. This is the effect of the RIS with the SWIPT. This is the SINR target. If we increase it, the quality of service will increase. And this is the sum power received. And we compared it with without RIS. So the range of the SWIPT will be increased much larger using RIS, which ensures the capability of RIS to enlarge the zone of SWIPT or charging the wireless. Here I just want to say, as a future work, if we just use passive RIS, if we used other type of RIS with other techniques, the problem will be more complicated, and I will consider it for future work. Second is the Isaac-aided SWIPT. This work is under review now in IoT Journal. And here we used Isaac integrated sensing to sense this target, and also for energy harvesting. And this is multifunctional access point. And our target is to improve the estimation rate ERE region, and it's important. So we use a trade-off function to optimize the sensing, communication, and powering. So we have 3 targets: sense, communication, and power, by using Kramer rower bound and the achievable rate and the harvested energy. We use the Mirage Surge Optimizer to prepare this multi-objective model, and we compare the Mirage Surge Optimizer with HA, Draco Optimizer Gradient Descent, H5N1, and code optimization. We evaluate using several metrics like achievable rate, Kramer rebound 2, transmitted power, and wireless received power. And the results demonstrate that Mirage Surge Optimizer ensured the efficiency to achieve better performance regardless to sensing and communication and energy harvesting. So our optimization problem here, we have the covariance matrix, which is R, should be larger positive values and doesn't have negative eigenvalue. And this first constraint means that the minimum amount of energy is given to energy harvesting receiver, which is gamma energy harvesting. And the Kramer lower bound is a lower bound of covariance of variance for any unbiased estimator. And then the total power of the covariance matrix TR should be less than or equal to W to make sure that the transmission coherence to hardware and in the regulatory limit. So we used Mirage Surge optimization technique, and the algorithm consisted of 3 main steps: initialization, and then we have superior Mirage strategy that search for a large range of targets, and then inferior Mirage strategy, and then we have to select the best targets for detection. So for some numerical results, we compared the Mirage with the other 5 benchmarks using objective function, and we found that Mirage achieves better results than others regardless to the achievable rate or objective function, and also for Kramer rower bound 1 and Kramer rower bound 2, and for transmitted power and wireless power. Also, this is a box plot for Mirage Surge Optimizer compared with the objective function, achievable rate, and other performance metrics, which confirms the efficiency of the Mirage Surge Optimizer. We compared also the convergence rate, and we achieved Mirage Surge Optimizer achieves better convergence rate at lower than 50 iteration. The last talk is part of the talk is the experimental result I did in Tokyo Tech in Tokyo. It's about over-the-air updates. And what is the over-the-air updates? If the car have a bug or error, most of the car vendors call these cars to the factory to fix this bug. And this will reduce the stocks of this company once they announce that, and also will take time because some of the customers doesn't exist, or they are traveling, they are busy, something. So the new technology of communications, we will have some smart roadside units that can download these bugs, and we have to make use of cars standing or waiting, and we made some practical experiment to make sure this download will be downloaded easily. We have to make a dual band because if some band is blocked, we can use other band. So in Tokyo Tech Smart Mobility Field, we use this test car. We mounted millimeter wave antenna and Wi-Fi 2.4 and 5 gigahertz antenna. And we made our measurement for small blocker. This car is a blocker, and for medium blocker, and for large blocker. And we took our measurements in different, this is the setting of the experiment. And then we have a fully line of sight. We discovered that 60 gigahertz have better performance. And the throughput, this is with the small blocker, and this is with medium blocker. Also, this is with large vehicle blocker, and with 2 blockers, the throughput will be reduced. But the idea is that the 60 gigahertz have higher throughput than others. And also we have the download latency performance for 10 gigabit update using 60 gigahertz and 1 gigabit update using 5 gigahertz and the 500 megabit update using 2.4 gigahertz. We found that the download latency for millimeter wave is 67.4 and it's larger for the Wi-Fi and 2.4 and 5 gigahertz. So our conclusion is that the programmable radio environment will improve the connectivity and wireless charging. We started with the SWIPT that enables simultaneous information decoding and energy harvesting. Then we moved to the RIS that handles bus loss blockage by shaping the propagation with low power reflecting surface. And then the ISAC, which environmental sensing, environmental aware for sensing and powering. And we know we need joint optimization technique for beamforming, resource allocation, covariance, and the design should consider the rate energy sensing trade-off. So the RIS-SWIPT will not only energy transfer technology, it will be intelligent, sustainable for sensing aware 6G IoT. For future directions, we have to embed reinforcement learning, online bandits, and lightweight AI for such techniques. And there is also open research challenge like scalable optimization of star active RIS, improved or advanced RIS types, and also the self-sustainable RIS operation, how we will balance harvested power, reflected energy. And of course, I'm trying to have a prototype validation and the benchmarks data set for RIS-SWIPT and ISAC-SWIPT and ambient RF harvesting. Thank you.
Questions? There's basically, I was going to ask you what you displayed in the last slide, which is the fact that a lot of these problems can be modeled with online reinforcement learning, and especially for modeling channel interference.
Yes.
And in general, for choosing parameters in transmission protocols.
Yes.
This is typically like a bandit problem, a multi-agent bandit problem. So I think that will be definitely, I mean, it's not a question, it's more a comment. It will be definitely an interesting direction to pursue because it's connects directly with machine learning techniques that have theoretical guarantees.
Yeah, I'm just in the start of the project, so I have to survey, and I found most of the solutions is AI or mathematical optimizations like alternative optimization, fractional programming. I have accepted the survey paper that we have a lot of tables. These tables, only 2 or 3 papers use reinforcement learning or deep reinforcement learning.
And you also mentioned federated learning. Are there specific privacy requirements in these applications that you can think of?
Yeah, of course. We don't need, there is some privacy, but we have to ease assumptions at the beginning, and then we increase system complexity. Of course, there is some privacy for the federated.
What are the private variables that you want to protect?
The users, the channel itself may be hacked by some other person, and the targets for sensing.
Okay, thank you. Thanks a lot.
Welcome.
So good afternoon and nice to meet you all. It's a great honor to be here and thank you for organizing this nice workshop. I'm Jingjing. So I'll be the last speaker today and of this workshop. Okay, so Before I start, let me just briefly introduce myself and our team. So I'm currently a third-year PhD student in the University of Osaka. And our lab name is called Machine Learning and Systems Laboratory. So if any of you are interested in our lab, please just scan the QR code for the details. And I'm under supervision of Professor Yoshinobu Kawahara. So here's a nice photo of him. Unfortunately, he couldn't make it here in person, so I'll just do my best. Also, Professor Kawahara is a team director in RIKEN AIP, and the team name is Dynamical Systems Learning. And our team mainly focus on the dynamical structure underlying data generating mechanisms, developing machine learning theories and algorithms for their prediction and control, and something like that. I hope you're not too tired. I'll do my best to make it as engaging as possible. So for me, my personal research interest is about time series forecasting, especially using some spectral modeling strategy. And also I'm super interested in building some intrinsic interpretable deep learning models, especially for such tasks like time series forecasting. So today's talk is going to be about our paper in AI-STAT this year. And the title is Dew-Former, Time Frequency Dew Domain Learning for Long-Term Time Series Forecasting. Okay, and I think this work is more empirical, so it's going to be very easy for you to follow. And this is like the overview of my talk. So first, I'm going to give you a very simple definition of what is the long-term time series forecasting problem. So given a time series X, which is always multivariate time series, so you can see the N is the number of variables, and here we have L, which is called the look-back window size. And the goal here is to predict the corresponding future T steps, also indicated as X hat. So for evaluation, we just simply use MSE and MAE, which are very trivial. So they are calculated on normalized data. And also for data sets we use, there are some very common benchmarks in this field. So like ETT or electricity traffic, something like that. I'll show the details in the next page. So one thing I want to mention is that these data sets, they are all collected or recorded from real-world sensors. So here's the details about those benchmarks. Like for example, for ETT, it refers to the electricity transformer temperature data recorded every hour or every 15 minutes, and also some electricity consumption data, and so on. So the frequencies are just very different, and the sum of this data can be very long. So that's why we call it the long-term time series forecasting. So this the details about the benchmark data sets. And so in this work, we mainly talk about transformer models. So the transformer models are very famous in the NLP area, or even in some computer vision tasks. But it can be very challenging when we directly use transformer models to time series forecasting. Because obviously, the first thing we might notice is that we're going to need some additional encoding for time series data, like instead of like positional encoding. So we're going to need something like maybe hourly, daily, weekly, that kind of time step encoding. And another big challenge is the quadratic complexity of transformer. Although it benefits from the self-attention mechanism to effectively capture the long-range dependencies, there will be a very very heavy computational cost. So the N here is the input time series length. So basically, in the vanilla transformer, which is this one, we have to calculate the self-attention score between each time steps. So it can be a complexity of O(n) squares. And there are many works have been proposed to try to address this kind of complexity issue. And they basically use some sparse attention, like log sparse attention, something like that. And also, those work, they try to change the tokenization of self-attention mechanism from the original point-wise tokenization to maybe like a sub-series-wise or patch-wise or even a variable-wise to reduce the computational cost. And there are some variants about this issue. And also, when we're dealing with very long-range data, the conventional transformers, they can lack of representation power. So there are some architecture-based innovation here. For example, some of the works, they incorporate frequency domain information for richer model representation. And also they try to model cross-variate or patch-wise dependencies. And also there are some works to apply multi-resolution feature learning via different networks, maybe some MLP networks or something like that. So this is basically the overview or the background of this field. And for our work, so our work is basically motivated by two key observations or two key technical issues here. So the first one, what we call it is the frequency bias problem or the spectral bias problem. So what we know is the self-attention mechanism, it actually acts as a low-pass filter, meaning that it tends to smooth things out and gradually erase those very maybe sharp skies and sharp spikes and very rapid changes in very short terms, which are also known as the high-frequency details. So there are actually many works to try to figure out why this kind of phenomenon happens. And some of the theoretical studies have shown that the self-attention matrix can suffer from rank collapse. So it eventually collapses to a constant representation, lead to the oversmoothing problem. And there are also some works that try to interpret the deep self-attention network by using the by describing it like a diffusion process. So where every layer it moves the token towards an attention-based mean, a local mean. So those high variance patterns or the high frequency information can vanish first. So those are about some theoretical results. But in our work, we try to explain and address this phenomenon structurally. So we argue that it happens because the conventional transformers, they treat all frequencies exactly the same as it moves through layers. So, those big patterns, like long-term trend, which always contain much more energy. So they can naturally dominate the attention scores so that eventually the high frequency details can fade away. And conventional transformers, they don't have some sort of built-in way to rescue or protect those high frequency details in very early stage. So that's the reason, and that's how we explain this issue. And I'm gonna introduce our approach to how to address this issue. And the second observation or the motivation of our work is that we can observe that most of the existing works, they tend to only look at the data either from time domain or the frequency domain. So it is very obvious that those two domains can be very complementary. So because time domain focus on capturing local temporal variations and frequency domain for global periodic patterns. So it is very natural that we suggest to combine them both. And here comes our insight. So we're trying to build a dual domain framework with layer-wise frequency modeling, which can address this kind of frequency bias issue. And so here's the overview of our proposed dual former model. So this dual former consists of 3 key components. So one time branch here and one frequency branch here in parallel. So at the very beginning, we have this hierarchical frequency sampling strategy that is for addressing the frequency bias issue. And what it does here is to basically assign different frequency ranges for different layers so that we can keep and preserve those high frequency details in the shallow layers or the bottom layers. And also after feature extraction by time branch and frequency branch, we have this kind of periodicity over weighting algorithm, which is for generating weights for these 2 branches. So we can, adaptively balance the contributions of 2 branches. So this is like the overview of our proposed model. And I'm gonna give you some details about each component. And so the first one is the main idea, the hierarchical frequency sampling strategy. So instead of look at all things at once, we decide to tackle different frequencies step by step. So as I mentioned before, top layers focus on modeling low frequency global information and bottom layers for high frequency details. So the implementation is actually very simple. So for example, in nth layer, we have this original spectrum indicated as WN. So what we do is to design a slicing function to dynamically select different frequency ranges for this given layer. And the sampled frequency range is just denoted as W tilde n. So the F here denotes the sampled frequency range. And we have this alpha here is called the sampling ratio, which is a hyperparameter that we can adjust. And the sampling intervals Pn and Qn, they are dynamically adjusted based on the layer index n, so that we can ensure a smooth transition from low frequency to high frequency. So the illustration is like here. So the Pn and Qn, they actually can be defined based on these 2 cases. So for example, case 1 is when this alpha value, when it is less than or equals to 1 over large N, we just simply define a uniform partitioning. And while alpha is larger than 1 over large N, we allow a little bit of overlapping between adjacent layers. So this is how we define this kind of slicing function and dynamically choose different frequencies for each layer. And yeah, this is the very simple idea of this sampling strategy. And the next thing is, because in the model, we have 2 branches here, but for time branch, we just simply apply the vanilla self-attention here, but with the sparse features, because we first do the frequency selection here. So I'm gonna skip the part of time branch and go to the frequency branch, because we have something new here called autocorrelation attention. So because I just forgot to mention that, but it's very trivial that time branch is for modeling temporal correlation, and frequency branch is for modeling those global properties and global patterns. So yeah, so the key part of frequency branch is this autocorrelation mechanism. So like unlike the pointwise attention in time domain, the autocorrelation mechanism here, it aims to conduct the dependencies discovery and the representation aggregation at the series level. So as you can see in this following illustration, it is like to compute the similarities between different subseries. And this kind of subseries similarity, or we call autocorrelation at time lag tau, can be computed in this equation. And based on the well-known Wiener-Khinchin theorem, it can be simply calculated in the frequency domain, like here, like in this equation. So this is how we calculate the autocorrelation in the frequency domain. And so how does this frequency branch work? What is the whole process? So basically, after selecting different frequency ranges for each layer, we have this sampled frequency, and we can compute the autocorrelation scores under various time lag tau, like this. So after that, we can just simply select the top K most informative lags. So these are the most informative time lags, tau 1 to tau K. And so after that, we just simply normalize those autocorrelation scores to probabilities using the softmax function. And this is actually very similar to the vanilla self-attention. And after that, this is like our attention score. And after that, we have to do aggregation. So here, to align with the current time step of our query, our queue, we use this kind of rolling operation that is just very simple to like cyclically shift the current V, the value, to align with the current Q. So this is called the rolling operation, and we just can do the time delay aggregation with the values. And we get the final autocorrelation score like this. And yeah, so after this, we get two extracted features from time branch and a frequency branch. So how are we gonna fuse them? So the idea here is to generate appropriate weights for the time and frequency branch based on the level of periodicity exhibited by the input series. So we want the model to be more adaptive to the current input time series. So yeah, so how are we gonna measure this level of periodicity? And here is an interesting phenomenon or observation, is that given this time series in the time domain and its spectrum energy distribution here, we can observe that periodic time series typically exhibits concentrated energy at a particular frequency and its harmonics. So we just thought that why don't we just use this kind of energy concentration as a periodic score, so we can give weights to our two branches. And then we have this kind of theorem 1, this harmonics energy lower bound theorem. So so the theorem is actually very easy to understand. So we have this continuous time series Ft and its discrete form, and we assume that this Ft can be decomposed into a very strictly periodic part and its residual. So the Fp is the strictly periodic component, and the Fr is the residual part. So we can easily define these following energies, like the energy of periodic part, energy of residual part, and energy of the full spectrum. And this is the energy of the harmonics. So given this basic frequency K. And so we define this harmonic energy ratio as, so this lambda is the energy ratio of the periodic part to the residual part. So we can get a lower bound for the ratio of harmonic energy to total energy in this equation, in this inequality. So as you can see, more like if the periodicity is stronger, then we can get a great concentration on the harmonics. So that basically means that we can use the harmonic energy ratio to kind of measure how periodic our time series is. And so based on this, we designed this periodicity aware weighting algorithm. So we just simply compute the harmonic energy, and we get this ratio, and we just use this as the weight of the frequency branch, because you know that more periodic the time series, and the more we can trust the frequency branch because it captures the global periodic patterns. So this is how we design this kind of adaptive weighting algorithm. And this is actually some visualization of how our model assigns or generates weights for the two branches. So one interesting thing here is that, here's totally 8 time series from 4 data sets. But you can see that in the first 2 rows, these 2 time series, they are actually different segments from the same time series. So the time point is from 0 to 600 and 600 to 1200. So this is like the neighbor. But as you can see that even though they're from the same time series, they exhibited very distinct periodic patterns. And as for these 2 rows, they are actually like the same location or the same segments of different variables of time series. So it's very easy to understand that they also exhibit different kind of periodic patterns. And so as we can see here, basically our model can generate and appropriate weights for those 2 branches based on the current periodicity level of the time series. So, but there's no ground truth that how periodicity this time theory is, but we human beings just can tell, like this one is much more periodic than this one, so the value is larger, so something like that. So that's how we explain this visualization. And also in the last part, I'm gonna show some main results of our experiments. So also one thing I forgot to mention is that so this long-term time series forecasting problem, we follow a very common setting that the input length or the lookback window size is fixed as 96, and for the prediction horizon, there are always like 69 or 192, 336, and 720, something like that. So here we just show multivariate and univariate time series forecasting results over 4 different prediction horizons here. So here's the average result. So as you can see, our proposed model basically outperforms the other existing models. So yeah, this is the main results. And we also did some further evaluations, like we try to design different variants of our due former to validate the contribution of each component. Like for example, we did it without the T branch, or did it without the F branch, or without the weighting algorithm, and something like that. So basically, this ablation study just confirmed the effectiveness of our model. And also for the sampling strategy, we did some additional experiments. So here is the result. So we do with just the local frequency, with just the low frequency, or just the high frequency, or the full spectrum, or we just randomly select frequency ranges for each layer, and we do this 4 types of ablation here. And the result just show that our hierarchical version is much smarter, like, because it can it actually align with the nature that the shallow layer of neural network is more is capturing the very high frequency details. And yeah, that is the ablation study we did. And also we showed some memory usage and running time result here. So basically, because of our dual domain, dual branch architecture, and also the frequency selection, so we use a sparse feature to do the self-attention. So we can actually, you know, yeah, okay, thank you. So yeah, so we actually show that our model is kind of efficient here. And yeah, that's all about my presentation, and thank you for your attention. Yeah, thank you.
Okay, so we have time for a couple of questions. So your model requires the time horizon as input.
Yes.
But is it? I mean, is it something that is you can do away with?
I'm sorry.
Can you sort of make it horizon free?
Horizon. What do you mean by horizon free?
I mean, just so you are simulating, you are predicting the time series up to a certain horizon.
Yes.
Which is a parameter specified by the model.
Yes,
so
yes.
Can the model, if like, can this be decided in at runtime? So I let the model predict, and then I stop it at some unspecified time.
Oh, I see. You mean like real time predicting?
Yeah.
Oh, I see. So that's not really what I'm doing, but yeah, it's possible. So here, what I'm talking is more like a sequence to sequence prediction or something like that. So yeah, you fix the look back window and you fix the future horizon. But yeah, definitely you can do some real time forecasting.
And is that the only parameter that you need, or are there any other input parameters?
Yeah, so actually that's a very good question. So so far our community just agree with the fixed lookback window size. But for me, in my opinion, the lookback window size, it should be a hyperparameter that we can tune based on the data sets. Yeah, so because we actually did some experiments about it that, for example, if the prediction horizon changes, the best input size, it changes as well. So yeah, so based on different data sets, and also based on how long you want to predict, you need to change how long you look back. Yeah.
Okay. Yeah. Thank you. More questions? No?
Thank you.